start recording. So let me start with an example. And I also said that there were two forms of this particular circuit, resonance circuit. One was called the series resonant and the second one was called parallel, and I said we will only talk about the series resonance, right? But that does not mean that you can ignore the rest of it. It may not be in the examination, but it's in the book and you are supposed to read through it because you're not here only to sit for the examination. So here you are. This is the first exercise I want to do. There is a AC circuit with a source, there is a resistance, there is an inductance, and there is a capacitance in the circuit. That the voltage is already in RMS format and it is R theta format, and this circuit has a current flow of I, and the resistance value is equal to 10, and L, which is the inductance, equal to 10 millihenry, and the capacitance value is 1 microfarad. So this is the question, and the first part of the question is asking a question to determine the maximum, right, maximum power which is dissipated by the circuit. So I have repeatedly told you that maximum signal power is going to be dissipated by the circuit which is completely resistant, right? Maximum. And we don't even have to know that, but we also understand there was a graph that we drew last time which told you that maximum signal power, there was a graph like that where this was basically the frequency, that axis was the power that is going to be dissipated, and I said that that's going to happen at omega star, where this omega star was 1 over root LC, and that was the maximum signal power that is going to be dissipated by the circuit. And we do realize that happens at resonance, and then at resonance the entire circuit is going to be resistive, so the total signal power that is going to be dissipated is going to be I squared, right, into R, or you could also have written it as V squared over R, right? You could have written it as V squared over R, because we already know V, and we know that voltage drop, when this goes this way, that's going to be over this way, this is going to go that way, this is going to go this way. These two will actually cancel each other out, right? So this entire voltage drop is going to appear across the resistance, right? This is very hard to understand, right? Now, in all the other circuits we say that if there was an element, there was some voltage across it. Here I am saying this is I, that is VR, this is VL, that is VC, this is equal to that and in opposite in terms of the direction. So when you add up voltage for that part, basically the reactive part is 0. So the entire V should appear across this, right? Appear across this. So we understand that would be P is V squared over R, which is 10, and that is equal to 100 over 10, and that is equal to 10, right? So that's the maximum signal. Oh, by the way, I written it down here. I think I did say in the class that all your books, the answer books can be located at this particular place, right? Check.com. I did say it in the class, right? Yeah, but the next class, group B said no, I didn't say that. I can sort of remember it. I said it. But please make sure, like I told the other people in that class, these answers are also worked out by humans, right? So there's always errors. So don't look at the answer and try to understand it. Try to do it using what you know, then look at the answer, right? So don't tell me that the answer you understood it wrong. Then the second question of this is, I'm asking you to find the bandwidth of the resonance circuit. Now I'm asking you to find the bandwidth of the resonance circuit. How do you do that? We already know that if I drew this graph of frequency versus the power, this is the maximum signal power. If I go down to the half of that maximum signal power, and where it is going to cross this graph, there are two frequencies, omega 2 and omega 1. Sometimes in books they call it omega high frequency and omega low frequency, and we told you that bandwidth was in fact equal to omega h minus omega L, or even you can write omega 2 minus omega 1. Now there is this huge equation, root of something blah blah blah, that's in your A4 sheet paper. Then once you take it, you have an expression that says bandwidth is equal to R over L, right? If you consider all that equations, you subtract, that's what you're going to get. This we did last time. Then R is equal to 10, and that is equal to 10 times 10 to the minus 3 millihenry, and then you would get 1 K, right, radians per second is the signal bandwidth. So there you go. So you have an equation, you just apply it. Then the part 3 of that question, you must have realized that I have uploaded some other problem sets from the book for this area. You have only 2 or 3 problems that you have to do, right? So please do them, because that's the type of problems that we can ask at examinations. Do you see that? We have a problem, right? I mean, a huge class with a small board, right? It's done already. Now, from I think next week, Professor Ranagiri will be using that what I showed you the other day, the multimedia projector, right? So good. Now you can see big words of what you didn't see all this time. Now you use, right? And we have already got 2 or 3 of those units. So starting next semester, there are no holes. Right? All multimedia projector, video recorded stuff. Video recorded I don't know, but multimedia projector. So in the third question, third part, I'm asking you to find, right? I'm asking you to find W1 and W2. Right? But this is very simple. Because why? W2 is R over 2L plus root of 1 over LC plus R squared over 4L. To be very honest, I have been teaching this subject for so long, I still don't know this equation. It's okay. It's in the book, right? And in your case, it will be in the A4 paper. So who would want to remember this? If you want to be a real, then you remember it, but it's not required, right? So that turns out to be, once you substitute R, L and C into it, 10.5 K radians per second. Then omega 1 is like minus R over 2L plus square root of 1 over LC plus R squared over 4L, and that turns out to be 9.5 K radians per second. And if you subtract from here to here, you should get this bandwidth, which you do, right? So no problem. Then I ask the question 4. I am asking you to identify value of I at omega 1. Now how to do this? Now I'm simply asking you to find this current flow in the circuit at a particular frequency. So tell me, how would you approach this? Now you realize this is an RLC circuit. I'm trying to ask you to find I. You have to convert this into an AC circuit, right? You convert this into an AC circuit. So to transform this into an AC circuit, the inductive reactance is equal to L omega. That's going to be equal to 10 times 10 to the minus 3, and omega, they have already told you omega, right? Like 1 times 10 to the 3. That works out for me to be 95 ohms, right? And in the same form, x of c, which is 1 over c omega, works out to be, this is 1 times 10 to the minus 6 times 9.5 times 10 to the 3, which is the frequency, and that works out to be 105 ohms. So now we are able to transform our circuit into an AC circuit. That is the capacitor, the resistor, and an inductor. So this is equal to 10. This is equal to minus J105. Remember, a capacitive, right, reactance is minus of XC. Then that is J times 95. If you are interested, you can also convert this into R theta type of format, and this is going to be equal to 105 with an angle of minus 90 degrees, right? And this is equal to 10 volts at 0 degrees. So you realize, if I give you the frequency, you can convert this into an AC circuit. Once it is converted into an AC circuit, very simple, you are going to apply the Kirchhoff voltage law. This current goes through that, so the voltage drop goes this way, this current goes through that, drop goes this way, current goes through that, drop goes that way. And here the voltage drop is going up. So we can write the Kirchhoff, right, voltage law for this loop. So it turns out to be 10 volts and 0, and all the others are, right, minus. So this is 10 plus J95 and minus J105, and that should be equal to 0, and I is in fact that. Right, minus J10. And this works out to be for me, which by the way the other group did the calculation and identified that value. It turns out to be, this is equal to 0.707 amperes at an angle of 45 degrees. So we have found I, that's what they want to find, right? Then E, so this is simple AC circuit theory. So if you know AC circuit theory, there is nothing serious about this. Then you have what is the power, right, dissipation by R, right, at this frequency. Now tell me, now I am asking you, what is the actual or maybe the average signal power that is dissipated across R? That is going to be smaller than the maximum signal power, or is it going to be more than the maximum signal power? Can someone tell me whether it should be smaller than the signal power, or should it be bigger than what we got earlier? What we got earlier was 10 watts, which was the maximum signal power. Is it smaller than that, or is it bigger than that? Anybody? Smaller? Is it smaller or bigger? Yes, smaller or bigger? Smaller, right? Because I said the peak happens at peak happens at the resonance, and anything else is smaller than that. You don't have to rocket scientist to say that. He was pretending not to see me, was looking at and hey, you were, right? Yeah, you're pretending not to notice it. So we realize that it is simply going to be P is going to be I squared times R, and I squared we know is 0.707 squared into 10, and that works out to be 4.9 watts, which is definitely smaller than what I had earlier. It's obvious, right? Then I'm asking you F to draw the phasor diagram. Right? Draw the phasor diagram. How to draw the phasor diagram for this? Can you quickly draw the phasor diagram for this? Right? How do you draw the phasor diagram? Chop. Draw the chop. You don't have to put the exact values. Show me the shape. Show me the shape. So I understand that would have been somebody after the class would have asked the problem question and he didn't understand, right? Makes sense, right? Otherwise you are in big trouble. So what is the baseline? What is the baseline? You folks are happy here at the back, right? Yes? Is it comfortable? Can you see, right? No, the problem is I can't see. So you can see the board. This is the class attendance is not much, right? Not much. Others have dropped out. So where is it? At least make an attempt. Okay. Okay, when you draw the phasor diagram, like what did I tell you? You always choose you always choose one parameter that is common to everything. So in this case, which is it? I. So first draw the I, and then on top of that, draw the V's. Here, the I is the one that is going to be absolute. So, okay, I got one person. I have to be happy with one person, right? Today I'll be happy with one person. So here, there are a couple of ways in which you can draw this, but since you already know I and its angle, here's what you do. You pick yourself a reference, angle of 0, sketch I. That should be 45, right? Yes, that should be 45. Then you realize resistance does not have you should not have a like a phase shift. So that should be VR. If you want to find the exact value, go do a calculation and find the value. Right? Then this should be VL. Right? Then that should be VC. You want to find the exact values? Fine. This is 90. That's what you should get for the phasor diagram. Is that okay? If you want to do it like in a proper manner, you would have found VL is equal to I times XL, right? Which is going to be equal to write it here, equal to 0.707 with an angle of 45 into XL, which was 95 with an angle of 90. That will give you 67.1 with an angle of 135. So this is 45 and 90. That is 135. See, 135. This should have been 67.1 is the magnitude. If you want to find VC, that is going to be I times X of C. That's going to be 0.707 at an angle of 45 times 105 with an angle of minus 90. That would have given you 74.2 at minus 45 degrees. See, that is minus, this is going to be 45, right? Minus 45 degrees from the reference. So 45 would have made the 90. So you want to do it like that, fine. If not, you could have just looked at it and then drawn the phasor diagram. Okay. Now the next part of the question, G, is I'm asking you to find the reactive power. Power across the inductor. Right? And I'm also asking you to find and the total reactive power. Power at this frequency. How do you answer that? How do you find the reactive signal power across the inductor? Yes, what is the equation you would use? How do you find the total reactive signal power? Yes. Not interested in trying them. What is the total reactive power? Okay, that's the equation. What is the total reactive power? So you have to remember that there were 2 or 3 equations that I gave, right? Reactive power. Oh, right? Q. So what is it? I gave you a couple of equations. The first was, if you want to find the reactive power, you have to find V times I times what? Sine of the angle between those two. That's the first method. Right? What is the second method? I said you don't have to do that. You can also use the equation I squared times X of L. Right? It is both. Now in this case, right, which one is easier to do? You don't have the B across, of course you have it because I already did the calculation. You can either do that, you can either use that, or the easier would have been to find I squared of XL. Right? So I'm asking you to find capital Q, not P, Q of L, which is I squared times XL, which is going to be I is right? So 707 squared into XL. XL was 95, right? Is that correct? Okay, so that gets you 47 watt. Now I realize that I'm looking at the notes that I did in the morning. In it I have used P and nobody highlighted it. Here it's P. See, nobody was paying attention in that class. It's Q of L. Then also, you know that, right? You know that IL or maybe I through that inductance is equal to 0.707 with an angle of 45, right? And VL we already have calculated here is 67.1 with an angle of 135. You could have also found this answer by putting QL is equal to V times I and the angle between these two, 135 minus 45. You would have got at least approximately the same answer that you got here. Right? If somebody can actually do this now and tell me, right? You should have got the same answer. Then they ask you to find the total reactive, right? Total reactive power. How do I find the total reactive power? Right? So my total, right, reactive power would be capital QL plus capital Q of C. Right? So I could have written it like what? This total reactive power here is what? It's I squared of XL. And what do I have here? Here, what do I have? I squared XL and plus what is the next one? Where is it? Yeah, what is I squared what? I squared what? Here, is it what? I squared of XC. Oh, capacitor reactor. I squared XC. Now the question is it plus or minus? Minus. Okay, fine. So I have minus I squared of XC, right? Or, so now you got some value, or you could have said the total reactance is what? Right? You can find the total reactance. Total reactance is what? J times 95, right? Minus J times 105. That would have given you, right? Minus J times 10. Right? Then immediately you can find QT is equal to I squared times 10, and that turns out to be minus. Right? So when you see this minus signal power, what you are going to think in your head is what? This system is more capacitive than inductive. Right? That's what you're thinking now. Because why? If you have minus reactive power, your system is going to be a capacitive system, and inductive systems, this reactive power is going to be greater than 0. So you get the same answer, right? Here also same answer, right? I squared XL minus XC, it's 95 minus 100, you would have got the same thing. I squared times 10, right? This is also wow. Wow. Right? There you are. Okay? So if I ask you to find the total apparent power, what is the answer you are going to give me? Total. Now you realize V for this whole circuit is going to be that, right? And I for this whole circuit is going to be 0.707 with an angle of 45. So the total apparent signal power is actually S, which is VI. That is 10 times 0.707, 7.07 volt ampere. Right? Okay? Are we happy? Yes? So this is the type of questions that we can ask from the resonance circuit area. Is that okay, folks? Anything I can answer before I move on to the next? There is also a second problem that I am supposed to solve, but I thought I'll leave it until next week, because if I do that also now, you are just listening, right? So that I will ask you to go home and look at these things, try it out, then you will come back next week. 2 weeks time and we'll start with this, right? Is that okay? Right? So let me ask another question while I'm here. G and H. H. I'll ask for the. No, I will. I have another question which talks about that. Okay. So if there are no other questions, I'm done. Right? With the dishonest. Okay. Sorry. Okay, there's another question asking me why we didn't use this minus 1 plus 1 before. If it is just one element that we are looking at, then we don't need to put the plus and minus. But if we are adding 2, then we have to make sure it is algebraic, right? So if it is inductive signal power, it is always going to be plus. If it's going to be a capacity power, it's minus. Right? Okay. Now let's get back to 3-phase. Now I said that in your 3-phase system, okay, problem solving finished, your discussions all over. Go. Do I have 3 people here that I can chase out to? Yes. Yeah. Yeah, you can go to beach. Long distance, but you can find. Okay. Let's get back to the 3-phase circuitry that we did. 3-phase circuitry. We started on 3-phase, right? 3-phase circuitry. We started and we gave you some equations which blew you away, right? Today is no different. Same thing is going to happen to you. Now, in the 3-phase system, you have Lakshmana, where the 3-phase signal is actually generated. Right? Here, at our house, this building, there's a 3-phase load. So, in fact, you have to look at this 3-phase system in 2 forms. One is going to be the generator, second one is going to be the load. Now, if I ask you, in a very broad sense, if I have a battery, right? If I have a right? So if this voltage drop goes from like minus to plus, where does the current flow? Is it from minus to plus or is it from plus to minus? It's plus to minus. So you realize if this is like a battery, somewhat of a generator, the I and V are in the same direction. But if it was a load, if this was your voltage, then immediately you know that the current is flowing in the opposite direction. Right? Now we are using this technique here. Now we will first look at the 3-phase generator. Right? If I look at a 3-phase generator, this is what we did last time. It looks like this. 3 voltage sources. I just want to introduce to you this notation, because why 3-phase is all about this notation. Once we get this thing right, notation right, rest of the calculations will come into you basically automatically. So this is A. So let's say this is the 3-phase signal that is generated, and 3-phase lines from the source generator goes out. Let's say that was A phase, this was B phase, that was C phase. Right? And then we also said that we will only talk about balanced 3-phase systems, which means all of these will have the same amplitude. So we said there was an equation that says EA, and this was capital N, and we said that EA of capital N, which is that voltage, right, EAN, was taken as the reference. So we said that there was a E maximum, I don't know what that is. Then of course we know E maximum. If you look at the signals that are going to come out of your AC thingy, how much is it? 230, 40, 240? That's EM, right? EM is about 240. So we can write that also down. EM would be around 240 volts. And we wrote it as sine of omega t. We took that as the reference. Then we said that there is this other voltage V of Bn, which we took as Em into sine, and then omega t minus of 120. So we took this B as 120, right, lagging, and we marked it going out like this. This was E of Bn, right? This is plus minus, this is plus minus. Then in the same form we had E of capital Cn, which was Em, and we wrote it as sine of omega t plus 120, right? This is plus, sorry, minus, this is plus, and that way it was E of Cn, right? Of course in some books we don't put the N because N is neutral. Everybody knows it's there. This, in certain books, this was just like written as EA, EB and EC, because we have an understanding that N is already there, right? It's already there. Now, so now we have part of it, and now each of these things are a signal generator. You will have a current that is going to go out, which is called capital A of N. This one you will have capital I of Bn. This one capital I of Cn. Right? Now again, when this goes out of your generator, it gets onto the line, and we'll call the other side of this line like simple A. This is going to be simple B. This is going to be simple C. So this current that is flowing through A to A is called I of capital A and small a. This is capital B and simple B. This is capital C and simple C. So now we got all those things worked out. A couple of more things. Then you realize that this voltage drop is from here to here. But looking at it from outside, so you also have the neutral line. Looking at it from outside, you can also draw a voltage drop from here to here, between the lines, right? And this is called E of AB, right? E of AB, see, E of AB, and then this is E of BC, E of BC, right? E of BC, sorry, going up, right? E of BC. Then you have the other voltage drop between A and C, which is going from here to here, right? Base AC going from here to here, right? I will not mark it because it becomes very cluttered. Now you have marked all of the voltages. Now we want to give these things, right? Basically definitions. We are going to call E of AN, E of Bn, and E of Cn. E of Bn, E of Cn, and all of these things are called like phase voltages, right? These are called by the name phase voltage, because why? All of these are associated with a single phase. And as a general rule, I mean, we understand EAN, EBN, ECN magnitude wise are going to be the same. So of course we know that E of AN, right, magnitude wise is going to be E of Bn, and magnitude wise E of Cn is going to be equal to E of M. Right? We already know this. We want to call this E of phi, which means phase voltage. And you also noticed that, you will also notice in the future, that if it is a generator, all voltages are denoted by capital E. So if you see that E, you know that is a voltage associated with a generator. Then we have E of AB, E of BC, E of CA. These things are called, right, line voltages. Because why? They are in between lines, not with respect to the it is not with respect to the neutral. It's with respect to some other line. Right? I'm going to show you that voltage is actually bigger than the phase voltage. Even when you look at the diagram, you can see it's bigger. Right? E is big, that's right? You should not look at it like that, but you know. Then you have I of AN and I of BN and I of Cn. Right? Those three are called phase currents. Right? Those three are called phase currents. And then also all of these things, if I want to now you realize EAB, EAC, ECA, all these magnitudes are the same. So if you want to put an expression which is like relevant to all of them, we need one like variable. So we call it E of L, simply indicating any line voltage, E of L. Right? Because we can't be writing for ECA a separate equation, E of like B in a separate equation. We can't write that now. So we write it as EL, which means it works for every single line voltage. Then this is called the phase current. So we call them I phi in, right? I guess in general. So then here you have A small a, you have I B small b. Then you have I, C small c. These are called, right, line currents in the circuit. Because why? This is IA, that goes in the line, this goes in the phase. But by looking at the equation, looking at the diagram, immediately you realize that IA of N is equal to IA of A. Right? Immediately you see that. And all of these things are called I of L, indicating it's going in the line. So immediately you realize I of phi is equal to I of L. We don't care, right? This is equal to that, that's equal to this, is equal to this. Rather than writing three equations, I can write like this: phase current is equal to the line current in this system. And then also I want to go back and tell you that this particular configuration is called Y connected, which I already told you last time, and also it is called a star connected network. So immediately you can create, or you can tell a very general statement saying that line currents are going to equal the phase currents when it is a star connected system. Right? Star connected system. Of course, there is also a second system which is called delta connected, which we will not go into. But it's there in the book. Take a look at it. Right? Probably next year they will start to teach you that. Then we have another little thing that I want to show you. Now you realize that E of AB, which is line to line voltage, is like nothing other than E of A of N, right, and minus E of B of N. How do you know this? Take a look at this. That voltage here, E of AB, if I apply the Kirchhoff law to this, is equal to E of AN minus E of BN. Right? That's what you have. So now this is not a simply a sort of resistive circuit, hence I have to add these things vectorially. Now how do I do that? Now to do that I have to first plot basically the phasor diagram. So this is EA of n, and I said this is E of B of n, and that is E of capital C of n. Every one of them is 120 degrees apart. Now, if I am going to take En minus of maybe Ebn, what I should do is this is going to be plus, and then minus Ebn is going that way, right? It's going that way. So I will write it as minus Ebn. Now you understand we have to use the regular parallelogram law to find out what is the equivalent or what is the resultant of these two. So here you are. I find the resultant, and that resultant is E of AB. Right? Now we do the same kind of analysis we did like last time. We are going to drop from here a perpendicular to this. You realize this is going to be, angle is going to be 30 degrees, and the angle here is going to be 60 degrees. I can use the simple Pythagoras rule here, and I can put down a statement that says EAB squared, this squared is equal to that's going to be this one going to square and plus this whole thing to the power 2. So I would rewrite this as like EM. Now remember that amplitude is EM, and that's the case for all of these things. So EM, I have sine of 60 squared. So this is 60 degrees, and I have to find this EM of like sine 60 plus I have EM. See here, this is EM, and then you have to add this little part which is going to be plus EM cosine of 60 degrees to the power 2. So if I expand this now, this is going to be EM squared sine squared of 60 plus EM squared from here plus 2EM squared of cosine of 60. See, this times that. Then you got plus EM to the power 2 cosine squared of 60, and this is equal. Now if you take these two together, that will give you EM squared, and this is, you got plus EM squared, and you got plus here the cosine 60 is half, that half and these two cancels, you got another EM squared. So immediately from this you will be able to see that E of AB is root 3 into EM, right? Root 3 into EM. So you realize if I take the amplitude of a single phase, if I want to find this, right, line to line voltage, I have to multiply it by root 3. Now basically if you take this household system, each of the single phases would be 240 volts, right? 240 volts. So if you take the voltage between lines, right, lines, that will be what? Root 3 into 240. Usually for a 3-phase circuit, in your advanced level, you would learn that line to line voltage is around how much? 400 volts. 415, 400 volts. Right? Now, can somebody, you have calculated, can somebody do this calculation? Root 3 into 240, how much is this? 415. See? That's how you got 415. Root 3 times that. But in the advanced level, they just told you, that's it. Right? 400 to 450. But that's how they got the answer. So in case you are in fact like, right, pondering, you realize something very important here. Something very important here. Here, if you take any of the, if you take EAB, right? If you take EAB, right? EAB, this magnitude of EAB is root 3 of EA of n. See, root 3 times EA of n, and it has an angle 0 was the angle of EAN, right? Here, if you look at this, this is EM with an angle of 0, this is EM with an angle of minus 120, this is EM with an angle of 120. So this was angle of 0. So here you can see it is angle of 0 plus, see, this is EAN, this is an angle of 30 degrees. So you realize for that particular phase, if you want to find this line voltage, it has a magnitude which is root 3 into the magnitude of the phase, and the phase has got shifted by plus 30 degrees. Plus 30 degrees. Now I want you to go home and do the entire thing. I want you to go home and do this entire thing. This was EAN. That was E of BN. That was E of CN. I am now telling you that this resultant, which is EAB, is root 3 of this with an angle of 30 degrees. If you do the same calculation for E of CN, if you do the same calculation for E of CA and E of BC, you would still get that is leading this by an angle of 30 degrees, that is leading this by angle of 30 degrees, that would be E CA, and that would be E BC, and this would be 30 degrees, that would be 30 degrees. Right? You go home and try this out and see. You do exactly the same thing I did for all the other two cases. You are going to get this triangle shifted, totally shifted by 30 degrees, and the amplitude is increased by root 3. So I can now write a very general statement. I can write a very general statement. Here's the statement I am going to write. E of L, which means line voltage, is always root 3 into the phase voltage, and any angle of the phase will be shifted by a plus 30 degrees. Now here, this was 120. This is 150. 120 plus 30. Over here, it is going to be this 180 plus 60. Right? 240 plus 30. 270. See? So, I can write a general statement. Any phase, you have the line-to-line voltage being root 3 into the magnitude and shifted by 30 degrees. That's how I'm going to write. So, if I am taking EAB, I realize phi is equal to 0. And E phi is equal to EA of n. And EL is equal to E of AB. Right? Then if I'm going to take E of BC, you realize you realize phi is going to be 240. Right? And E phi is going to be E of BN. And you realize EL is E of BC. So you realize this equation that I'm going to write is applicable to anything as long as you substitute the right values for the phi and L. So this is a very, very important equation that you have learned. Root 3 times E phi, the angle of the phase plus 30 degrees. Right? plus 30 degrees. So very important equation that you have actually written. Now, right? So this again is something that you would write in your A4 paper. Hopefully we know how to use it, right? But this is what you're going to write in your A4 paper. Now, let's look at, right? So at this particular instant, you have learned 3 new things. Right? You have learned 3 new things. The first is what? If you have a star connection system, the line current is equal to the phase current of the system. That's the first thing. Then you have also understood that line voltage is √3 of the phase voltage. Right? Then you have realized that it has got shifted by an angle of 30 degrees. Right? So those are the 3 things that you have now identified in your system. Okay? Now I want to ask you, I want to take you further. So now we'll start talking about power. Right? Now you have a signal generator. Right? You have a signal generator where you have EM, right, with an angle of maybe, I don't know, something like theta V, that is going to generate your signal. Then through that signal you are going to you are going to generate for each of the phases a current that is going to be equal to some IM maximum value with an angle of basically theta I. Now the power calculation that you did for your AC theory is directly applicable here. So how do I do that? So you would write P for A, which means A phase, like a single phase. You will write, now rather than putting it like this, I would write E of the phase, right? Or maybe I can write it like this, right? For each of the phases, you have a voltage from that phase. You have a current from that phase, and cosine of the angle between E and I, and that will be in terms of what? Now this is for a single phase. When we do an actual value, when you substitute calculate, you will see how this comes out. But for each phase you have an E and you have an I. So that's what you would get for the power. If I want to calculate the total signal power, and since we are using this balanced circuit, this has to be multiplied by 3 because all phases will have the same amount of power. So it will be equal to 3, right? 3 times E phi and I phi cosine theta, the angle between E and I. See? 3 times that. Each phase will have the same amount. Now let's play a little trick. Now we know that for a star connected system, we know that I phi is equal to IL. Yes? We know this. I phi is equal to IL. And then we also know that E of L is equal to √3 into E of phi. We just said that. If I now take these two and I substitute here, I will get an expression that says 3 times E phi is equal to EL over √3, right? EL over √3, and then you have I phi is equal to IL cosine theta, the angle between E and I. This √3 is going to cancel with this. That's going to give you root 3 ELIL cosine of theta times EI. This is the next very important equation that you are going to learn, which is exactly equal to root 3 times an ELIL of cosine theta between E and I. This is also a very important expression, right? Very important expression. So if somebody hands you only the voltage or the phases, I use the first part of the equation. But if somebody gives you the line voltages, I use the second part of the equation. Both answers I'm going to show you at one point in time are the same. Both answers will be the same. Now, can you tell me the expression here? What would be the reactive signal power? Reactive signal power. Now, you don't have to be a genius to say that. This is going to be equal to 3 times E phi I phi. Rather than cosine, you will have that. Right? I don't even have to prove it. Then this would be root 3 times, you got this ELIL and sine of theta, the angle between E and I. I don't even have to prove it, but you know by default that's what you're going to get. Right? Okay. Now we have completed the three-phase generator. Now when you take a three-phase load, the entire set of calculations and the expressions that you will obtain are exactly these. Right? They are not different at all. They are simply going to be this, except the notation is going to change a little. Right? Let's look at it. We'll do that and then go for a break. Right? Here is so here is a three-phase load. Right? If you have a three-phase load, generally in books they draw it in the other side. Right? So here is a three-phase load. Box because it is an impedance. Box. This is called A. Like simple A. Anytime you see a simple A, we are talking about a load. Anytime you see a capital A, they are talking about a generator. This is small n. This is equal to ZL. This is equal to ZL. This is equal to ZL. Why? All three of these loads are going to be equal because we are talking about balanced loads. When you go into the next year, they will be talking about unbalanced loads in the course that is called electric circuits. Then you learn slightly different than this, but this is the easier one to handle. So we are only going to introduce you to balanced circuits at this level. This is B. This is C. Right? C. I mean, here's how they do it usually. This is A. It's going hooked up to the A in the generator. This is B. In most books what they do is they put a thing here and call this C so that the ABC will remain in that order. Right? Now again, we do the same thing that we did earlier. Here, this is IAA. It's the same thing that you saw earlier. This is IB small b. This is I capital C and like simple c. Here you understand that will go in, so the voltage drop is going to be V of AA. So everything associated with the load is V rather than E. If you see V, we are talking about the load, right? Then in the same form, this would be V of A V of Bn, that's minus, this is plus, there's an arrow, this is V C of n. Right? Then over here you would have capital I, small a and n. Here capital I B and n. Here capital I C and n. All of the lettering is going to be simple. Then we are talking about a load. All the other expressions that you're going to have will have the same format. Say for example, V of AB, V of BC, V of CA are called the line voltages. In the earlier case it was E and AB. Remember, E of capital AB. Then you have V of AN, V of BN, V of CN. These are called phase voltages. Right? Exactly the same. Then you have I of AN and I of BN and I of CN. These are called phase currents. Then I of AA and I of BB and I of CC are called line currents. Just like in the earlier case, line value of the current is the same as what goes through the phase. Right? No different. So if you know one, you know the other. Then you can also write down a very simple expression. You can also write down saying V of the line. Right? V of the line is equal to root 3 times V of the phase and the angle of the phase plus 30 degrees. The only thing you have done here is replace V with that. You have actually replace E with an V. That's it. Right? All expressions are the same. Even if you draw the phasor diagrams, they are the same. Phasor diagrams also the same. So now if I take the full thing together, this is how it's going to look like. Right? If I'm going to put the full thing together, I have a source, and over here I will have a load. Right? I will have a load. This is A, that is B, this is C. This is small a, this is small b, that is small c. This will be hooked up to that. B would be hooked up to that. Then you have like C hooked up to that. That's a full three-phase system. If you want to make it very hard, you can include here a line resistance. But we are not going to do that. If you look at the book, there are some problems with line resistances included. But let's say, no, we don't have any sort of line resistance. When you look at this, you are going to realize that E of AB is equal to V of AB. Right? So E of AB between these two lines should be equal to what is between these two lines. Right? In the same manner, you have E of BC being equal to V of BC, and E of capital CA is equal to V of CA. Right? These are things that you can look at in the diagram and recognize. Now what we are going to do is, once you are back, we will do a problem and see how it works out. Okay? Okay. So go out for, we have plenty of, because I have only another one problem to do here in the class. and I stopped for the other people at that time. And when I stopped, there was about 15 minutes. Now for you, there's going to be more than 15 minutes left. Right? Because I think there, it took a long time, because if you had upset me, I chased people out and give a lecture. Everyone listened 15 minutes of lecture. So that 15 minutes plus the other little thing is would have taken a longer time. Right? So here's what you can do. Use this opportunity. If you have any problems, once I finish this one, which is the same that I did for the other class, if you have any problems to solve, any questions to ask, I will spend my time answering this. Right? So when you go for tea, quickly drink a cup of tea, come back and figure out any questions that you want to answer, finish this, I will answer it.